Good morning, good afternoon, good evening, mammals. This video is kind of sort of for NTI day number 11, which is Thursday, March the 26th. Like I said, I'm posting a problem set out there. I'm actually going to extend that, and let's let that be due through Tuesday. So you're going to have lots of problems to work on for the next few days. This is just the last kind of problem that you'll see. Yesterday's video was carrying on long enough as it was, and I didn't want to tack this on there. We'll be dealing with radioactive decay, which is really just a special case of first order reaction. So I'll be doing math with the equation that I introduced to you yesterday for first order equations. The AP exam used to go into a lot of detail about kinds of radioactive decay. I'm just going to quickly gloss over it here. If you've ever thought about it, the nucleus being composed of a bunch of positive protons in a very, very small space, the electromagnetic force says that that shouldn't be a thing because all of these positive charges close together are going to repel each other. Well, there's another force called the strong nuclear force, which makes protons attracted to neutrons. So what we're looking for is having the right ratio of protons to neutrons so that the attractive force from the strong nuclear force counterbalances the repulsive force from the electromagnetic force. And radioactive decay occurs whenever we aren't in this kind of sweet spot Goldilocks zone of equal amounts of attraction and repulsion. Alpha decay occurs in elements where there are too many protons, not enough neutrons, so too much repulsion, not enough attraction. And it helps to bring the ratio of protons and neutrons in line by emitting an alpha particle, which is basically a helium nucleus. 2 protons, 2 neutrons. So an alpha decay occurs because we're emitting 4 nuclear particles. The mass number goes down by 4. And since 2 of them are protons, our atomic number goes down by 2. What you can notice here is that we are conserving mass in every way. 238 total mass number on this side, 238 total mass number on this side, 92 total atomic number, 92 total atomic number, no charge, no charge. And by emitting this brings the ratio of protons and neutrons more in line, and alpha decay will occur until it reaches, like I said, an area in the sweet spot where the attraction and repulsion are roughly balanced. Beta decay occurs in the opposite situation where you have too many neutrons, too much attraction, not enough repulsion, and it's pulling the nucleus in too tight. And what occurs in this situation is that a neutron converts itself into a proton and an electron, and in the process kicks out an antineutrino, which is just a high energy particle. So the new element's going to have the same mass because a neutron is converted to a proton. They both count in the mass number, so 14 and 14. And we've gained a proton, so our atomic number will increase from 6 to 7 because we switched a neutron to a proton. Electrons balance this out because we write the electron nuclear symbol with a -1 atomic number, so it still conserves mass by saying that we have 6 atomic number on both sides. Anyway, if we have time to kill on future NTIs after the test date, maybe we can go into stable and unstable elements. I think it's kind of cool, but for now, let's just do the math that you might see. Okay, I want to give myself some extra room to do this. So we have some carbon-14, which is a radioactive element of carbon, and it's decaying, and it has a decay rate of 1.21 times 10 to the -4th. So since we're first order, I'm going to be setting up my equation here. And I'm going to fill in my K. And they're wanting us to solve for T, for how old it is. And what they've told us is that 70% of its original amount of C14 is remaining. So here's the nifty little math trick on this. I'm going to say that the initial amount was 1, so natural log of 1. And if I have 70% remaining, then I'm going to call the amount that I presently have 0.7. And this is a nifty trick because natural log of 1 is 0. So that simplifies my math. Because now to get my answer, it's just natural log of 0.7 divided by 1.21 times 10 to the negative fourth equals t. Let me check my calculator. Wake up. And that is 2,948 years. Should have given you some time unit here. The K on this would be in per years. Sorry about that, but that's how I knew that this would be in years. I should have labeled that. Okay, second problem is going to be a two-stepper, and it uses a kind of special equation that's on your formula sheet that's derived really just from algebra from this. So let me show you how it's derived. So back to this guy. Okay, so half-life implies that half of it has decayed. So I'm going to let this one be natural log of 2, and then if half of it is decayed, this is natural log of 1. And I'm doing that so I can make my same math trick of letting this guy be equal to 0, so I don't have to worry about him because it's equal to 0. And then natural log of 2 is approximately 0.693. So the AP formula sheet has this equation, T1/2 equals 0.693 divided by K. So if they give you a half-life, and that's what this is, a half-life, this is your way to turn it into K. So this problem gives us a half-life of americurium, or americium, I forget exactly how to pronounce it, and it's 243 years. And I'm going to need to use this equation to turn that into K, so I can calculate the amount remaining at 76 years, which is not exactly evenly divisible by my half-life. So my first step is to use this to get a K, so I can plug that back in to this equation there. So 243 equals 0.693 over K. Wake my computer up again. That gives me a K of 0.00285. Now I have K. Oops, not the pointer. Now I have K. I have T, which is 76 years. I have my initial amount, and I want to know the amount at 76 years. And the nifty thing about this is we can treat masses like concentrations, so I can plug in a mass into that and it's going to work out okay. So let's go ahead and solve this out. So I'm looking for this amount. my initial amount was 2.5 times 10 to the negative sixth. That equals 0.00285 times 76. And the units on this, since it was in years, would be in per year. And so that's, when we multiply by this, we get a dimensionless quantity because it's per year times a year, which is why we can use masses or concentrations over here, because we just get a dimensionless quantity, and as long as we're consistent, it's all going to be good. So natural log of A equals 0.00285 times 76 plus natural log of 2.5 times 10 to the negative 6. So I added this to both sides to cancel that out. Natural log of A, crunch my numbers on that, I get negative 13.116. And if you remember how to get rid of the natural log, I'm going to take both sides to the e power. So raising this one to the e and this to the e, that cancels that. So I have A equals e to the negative 13.116, which is 2.01 times 10 to the negative 6, which makes rough sense to me because 76 is well under a half-life of 243 years. So in 243 years, I would expect half of this amount to be gone. So I would be looking at like 1.25 times 10 to the negative 6. And so I didn't get all the way to a half-life, so I'm expecting more than 1.25 times negative 6, which I have. So anyway, that wraps up kind of this special case problem for radioactive decay, which is just doing some algebra with first order equations. So I'm going to close it off here. I'll get the problem set posted up, and that'll be the last thing that I post until Wednesday. So just hit me up with questions as you need them to get those problems done, and then we'll be moving on to some kind of summative assessment, and then on to our last unit. So, as always, take care of yourself and others, practice good hygiene, and I'll see you on the flip side.